Hi, everybody. Welcome to our first lecture on Chapter 6, and also welcome to the material after the midterm exam. So we have some new material that we're going to present today, and I also just want to sort of step you through some of the changes that I've made to the Moodle pages and how the PowerPoints will correlate with what we're doing in the lecture material in terms of the book, because they're not exactly the same. The first thing I would like to alert you to is the fact that the PowerPoints do not correlate directly to the textbook. The first set of PowerPoints talks about inductance, and that would be from section 6.1, and then also from part of section 6.3. So at the same time, the second set of PowerPoints correlates to section 6.2 and part of 6.3. We are not covering the rest of chapter 6. We're just covering inductance and capacitance and how you combine inductors and capacitors in series and parallel. So the mutual inductance material that's covered later, we're not going to have that as part of our course material. The other change that I wanted to make you aware of is I've changed the due date of the chapter 6 homework. I'd originally had it, I think, for March 21st or March 24th, and I just realized it was not quite enough time to sort of get back into this important material. So right now the date is going to be March 28th. So the homework is, as always, underneath the Submit tab, so that you can see the problems that are going to be required of you for your homework, and that will prepare you for the final exam. So those are just some of the deals that I wanted to alert you to. Also, as I was putting together our Moodle page, I put together two charts from our PowerPoints that compare inductors and capacitors. And I just thought these were really, really good in terms of a summary of how to approach problems and how to read circuits and just how to get started with your work. All right, so the caption at the top of this label tells you that inductance is the tendency of an electrical conductor to oppose a change in electric current flowing through it, and it's measured in units of Henry, while the capacitance is the ability of an object to store electrical charge measured in farads. Now, it turns out a farad is a huge unit, and so we generally talk about microfarads or picofarads, but always the idea of a farad. So if you look at these two charts, you'll see some good comparisons. You'll also see the information that you need to step you through working with inductors and capacitors. All right, so having said that, I'm going to bring up the first set of PowerPoints. And like I said, this set of PowerPoints actually covers section 6.1 and part of section 6.3. So when we talk, so in other words, chapter 6, part 1 says inductance, capacitance, and mutual capacitance, or mutual inductance, whereas actually we're just talking about inductance in this section. So over the course of some of this, we're going to talk about these different properties. And when we start talking about inductors, the variable L refers to inductance, which, as I said, is measured in Henrys, and an inductor is just shown as a coil. All right. So inductors are sometimes, they're all over the place in electric circuits, and sometimes they're just called coils, because if you look at physically at an inductor, they just tend to look like a little spool with a bunch of wire wound around it, because the creation of that field is where all the magic happens. So you have sort of a field based on that winding of the wire. And so an inductor and a coil is, well, the terminology is used interchangeably. However, the real name is inductor. All right, so if you look at this equation, it says voltage as a function of time is equal to inductance times the first derivative of current with respect to time, dIdt. So it says, what if the function of what if I as a function of t is constant? Well, if you look at this equation, if I of t is constant, dIdt is equal to 0. So that means that anything times 0 is going to be 0. So v as a function of t then would also be 0. All right, so if the current in an inductor is constant, its voltage drop is 0. And that means that you can replace an inductor with a short circuit. In other words, that would be its function under those circumstances. So the equations that we will use are all spelled out for us in the chapter and on the tables on our Moodle page. And just asking a question here, we just showed that the current in an inductor must be continuous for all time. That means that the voltage must also be continuous. That's not true. It actually regulates the change in voltages, or regulates the change in current. And so the voltage is not a constant. So it's sinusoidal or cyclic or whatever the particular nature of the wave is. Okay. So if we look at this equation, we integrate it, we can come up with a function of current or amperage and current as a function of time in terms of the inductance in that particular inductor or coil. All right, same with the power. We just go ahead and create this because we know that power is equal to V times I. And so we can come through and come up with the equation for power. And then by integrating again, we can come up with the equation for work. All right. So what are inductors? Inductors are energy storage devices. If the initial current through the inductor is not 0, then the inductor is storing energy. Pretty simply put. For this, suppose the initial current is 2 microhenries and the initial current is 1 amp, is a 2 microhenry inductor. Using those equations, you can see that the initial energy stored would be 1 microjoule. And you just go back to the equation and there you go. All right. Here we said, is this voltage continuous? Well, I at time 0 is equal to 0, and I at some other time is equal to 8. I at time 0 is equal to 8. You go through the equation, you'll see that it continues to be 8. And so it is continuous. So if you find the voltage, you can use the voltage equation based on the 4 microhenry inductor. And once again, make sure you put it in base units. So 4 microhenries is 0.004 henries, and you come up with a voltage equation. So if we look at this, is the voltage continuous? It is not. All right, continuing here with another example, we're calculating the power. So these PowerPoint slides just show you how to use the equations through an inductor so that you can develop these. Then we have the energy associated with it. I guess I should note the power here is in watts, which is a good unit for power, right? The energy is in joules or microjoules. So once again, or millijoules. So it's still a good unit. All right, now this is actually the material that comes out of section 6.3. If inductors are connected in series, it turns out that the inductance of each of these add, right? So they just go through the Kirchhoff's voltage law and develop this equation. But the basic takeaway is that inductors in series add. What if they are combined in parallel? Well, then it's that 1 over average, just like with resistors in parallel. So you can think about adding inductors in series. It follows the same rule as adding resistors in series. Adding inductors in parallel follows the same rule as adding resistors in parallel, which we learned back in chapters in the first part of our test. All right, so here's an equivalent circuit. You'll do this, break it down just by circuit diagrams. and you'll be sure to see something like this on your quiz or your final, where you reduce that, the two inductors in parallel and find an equivalent inductor, and then you have it in series with another inductor. So adding them together, come up with those equivalents. All right. So the next two, we have this summary of inductors, which is half of the material that I have put on your Moodle page. I've just combined it with the material for capacitors. So these are the two charts that have the inductor part of the charts that are on your Moodle page. All right, so I think at this point it would probably just be wise to continue with the second set of PowerPoints since we've had a pretty good start with inductors. Let's just move on to capacitors. The PowerPoint slides are written to be quite similar in structure for inductors and capacitors. So when we look at the PowerPoints for our, I want to get a different share. I apologize. When we look at the PowerPoints for our capacitors, once again, section 6.2 and 6.3, you'll see that the structure is very similar. All right. So what is a capacitor? Well, the first thing is a capacitor is the diagram for capacitor is a straight line followed by a beginning parenthesis. Okay. And a capacitor stores electrical charge and is measured in farads. So the basic governing equation for the capacitor looks like this. I as a function of T is equal to capacitance in farads times the change in voltage with respect to time. So if you look at that, you'll also see that that equation looks very similar to the equation for an inductor, except that V as a function of T is swapped out for I as a function of T, and that di dt is swapped out for dv dt. So in other words, the voltage and amperage positions change in the equation, but the structure once again is still the same. So just like we did before, we looked at a situation where we had di dt is a constant, or is a constant, and so we determined that v of t, or that voltage would be equal to the v of t, the voltage as a function of time would be equal to 0. See, with the structure of this equation, it works exactly the same way. If dv dt, if v of t is constant, dv dt is 0, and I of t is also equal to 0. All right, so it's a little bit different because if the voltage drop across a capacitor is constant, its current is 0. So remember, if the voltage is 0, it means it's a short circuit, but if the current is 0, it's an open circuit. All right, once again, just talk a little bit about the nuances of this equation, and the structure once again is quite parallel to the structure of the material for inductors. Okay, here we just use the equation to determine a voltage drop across a capacitor. And once again, the units are very consistent as long as you make sure not to use a prefix or a power of 10. If you use farads and if you use henries, your units are all going to work out beautifully. So that's kind of nice for those of us invested in the crazy English system of units. It's nice to have everything just work out in the end. All right, so here we go. We integrate this equation to come up with V as a function of T in a capacitor. And then we come up with the power equation and the energy equation, just like we did with the inductor. Okay, so the punchline here is that capacities, like inductors, are energy storage devices. But if the initial voltage drop across the capacitor is non-zero, then the capacitor is storing energy in the same way with an inductor. If the initial amperage across the capacitor, current across the capacitor is non-zero, then the inductor is storing energy. All right, here we go. Initial voltage drop across a 4 microfarad capacitor is 10 volts. What's the energy storage? Well, you just, first of all, change this into farads, use the energy equation. You'll come up with 200 times 10 to the minus 6 joules, which is 200 microjoules. All right. This slide, once again, we're finding the voltage, power, and energy. Just use those equations across that 0.2 microfarad capacitor. And similarly here, just finish off that work. Okay. So here we have an example that during this interval between 0 and 40 microseconds, the power is positive, meaning absorbed, which goes along with that passive sign convention that we are still working with, but that we learned back in chapter 1. The energy is stored or trapped by the capacitor so that even when the current goes to 0, the voltage stays at 10 volts, which is pretty cool. And the energy is non-zero as well. All right, so here are some functions of different properties versus time. Here is current versus time, power versus time, voltage versus time, and energy versus time. So you can see how those work. Go to 0 here, right at 40. Go to 0 here at 40. Continue as a constant beyond 40, and continue as a constant beyond 40. In microseconds, 40 microseconds. All right. So when we start talking about capacitors in series, the first thing is we find out the capacitors in parallel add. So unlike an inductor, where they add in series, capacitors add in parallel. Capacitors combine in series like resistors, or inductors combine in parallel. And I should emphasize that sentence differently by saying capacitors combine in series, like resistors or inductors combine in parallel. All right, here we want to find the equivalent capacitance for the circuit. Once again, we know how they combine in parallel. We know how they combine in series. So we find the equivalent by first combining these two in parallel, then combining that equivalent with this in series. All right, so here are the charts that I've actually put up on our Moodle page that compare inductors to capacitors, the symbols, the units, the describing equation, the other equations, the initial conditions, the behavior with constant source, short circuit versus open circuit, the continuity requirement, and then on the next page, the equations for power, energy, initial energy, trapped energy, and the equations to how they're described when they're connected in series and when they're connected in parallel. All right, everybody. So that is the end of our short foray into section 6.1, 2, and 3. Like I said, please ignore the rest of the material. I've posted lectures for each one of those topics, inductors, capacitors, and the combination, but this lecture serves as a good overview. I think these PowerPoints are especially good based on the way that they build on what we already know, not what we already know, but the structure of how we've learned just resistor voltage, resistor battery, power source circuits. So this just is a nice continuation. So everything's posted. You have a little bit more time than I had originally stated, and good luck with chapter 6. So we'll do a lab this afternoon, getting started with the lab on inductors and capacitors, which will continue through next week. And if you have any questions, let me know. Talk to you soon.